Exercise 231 says fingolimod is a novel drug that has recently been developed for the treatment of multiple sclerosis. This is the cause of this isn't completely sure just yet as of 2020, but it seems to be a viral infection that destroys the fat coverings around your neurons. Then your neurons don't fire as efficiently, and so you lose the function where the neurons work. So sometimes people will become paralyzed, or sometimes they'll get dementia. So this drug, fingolimod, is meant to treat that. In April of 2008, researchers reported the results of phase 3 clinical trials of fingolimod in which 70% of patients who took the drug daily for 3 years were relapse-free. So the fat that wrapped around their neurons wasn't getting destroyed anymore. This is a tremendous improvement over previous drugs that only prevented relapse in 30% of patients, so 30% to 70%. Draw a resonance structure of fingolimod. So this is using a sort of real-life molecule, a biologically active molecule, to visualize a resonance, but the procedure for identifying the resonance that's there is the same as in the simpler molecules we were viewing. First thing you want to do is to fill in the lone pairs, because lone pairs are essential for a few of the resonance structures. There are lone pairs that are required to have the resonance. So I filled in the lone pairs to give all the oxygens and nitrogens 8 valence electrons, 8 electrons around them. And now we want to work methodically from left to right across this table to see what resonance patterns we have. So first, we have an allylic lone pair. That's a lone pair that's one atom away from an atom in a double bond. Well, we have lone pairs, and we even have double bonds, but they are not close to each other. They're not one atom away. These would be allylic if you had a pi bond here. You don't. These would be allylic if you had a pi bond 1 atom away, so right here you don't. These lone pairs would be allylic if you had a pi bond 1 atom away. That could be here, here, or here. You don't have any of those. None of those lone pairs are allylic, and so we don't have this first resonance pattern. An allylic positive charge, we don't have any positive charge in this molecule, and so we can't have that one. Lone pair adjacent to a positive charge, again, we don't have a positive charge in this molecule, so we can't have that resonance pattern. A pi bond between 2 atoms of differing electronegativity. You're really looking for a pi bond to nitrogen, oxygen, fluorine or chlorine. Most often it would be nitrogen or oxygen. Here we don't have that. We do have nitrogens and oxygens, but we don't have any pi bonds to them. So we don't have this last one. So that leaves us with the 5th pattern. This fifth pattern is very unique. It usually stands out because you'll have a ring and you have what are called conjugated pi bonds enclosed going all the way around it. This term is an important one, and it'll come back in organic chemistry too for a whole chapter. So it's worth taking a second to talk about. Conjugated pi bonds are pi bonds that alternate between single bonds. So for example, you'd have double, single, double, single, double. So you have these pi bonds here that alternate, that are separated by one single bond. The significance of that is that, remember, pi bonds form when you have 2 parallel p orbitals on adjacent atoms. So these p orbitals all have to exist to create these pi bonds. But notice that when you visualize them like that, you can tell that there are 2 parallel p orbitals also where it looks like you would have single bonds. So when you have these alternating single and double bonds, or these conjugated pi bonds, the electrons in them are able to spread out over the whole series of conjugated bonds. So all of these lobes would overlap, really help to spread the electron density out and make the molecule more stable. Remember, the significance of resonance is twofold. First, it shows how much electrons are spreading out, so it gives you information on stability. And the second thing is it gives you information on rigidity. How rigid is the molecule? Because these pi bonds, or these partial pi bonds, can't rotate. So the bonds can't rotate anymore, so the molecule becomes more stiff. And these are essential features for messenger molecules. If a molecule has to be made in one place and then travel across a body and communicate a message in a far different biological place, it can't be very reactive. It can't react from as it travels from the place where it's made to the place where it's communicating the message. So it needs to be stable. So resonance helps with that. It also needs to be rigid because you have a receptor site, and in order for the messenger molecule to fit in there, it has to have a reliable shape. If all the bonds can rotate, then it'll be like a piece of soft spaghetti in boiling water, constantly waving its arms, and it will only fit into the receptor site sometimes. But if the molecule is rigid, then its shape will be reliable, and it will reliably fit into the receptor site and communicate the message. So because resonance gives stability and rigidity to molecules, you see resonance in a lot of biologically active molecules. And that's especially true for this last one, because the ring adds even more rigidity. So not only do you have a lot of stability, but you have a lot of rigidity, and you'll find the six-membered ring with conjugated pi bonds, and even other rings with conjugated pi bonds. You'll find them in so many biologically active molecules. For the six-membered ring, you'd find it in everything from dopamine to Prozac. And for other conjugated pi bonds, you have in things like caffeine or adenine, or the 4 base pairs in your DNA, because you want those to be stable too, so adenine, thymine, cytosine, and guanine. So really important biological pattern is this fifth one. Now notice in this ring, you have these p orbitals that would be parallel on every atom in this ring to create those pi bonds that are drawn. So really the electrons here spread out over the whole ring. And sometimes you even see this ring drawn as a six-membered ring just with a circle in it. And that's trying to symbolize the extra stability and rigidity that's added to that molecule because of resonance. Well, if you look back at fingolimod, we now get a slight better appreciation for why it's a great, or why it is so biologically active. It has that fifth resonance pattern here. So we do have resonance, it's that fifth pattern. We have to warn the world, so we draw those big brackets, tell people all the molecules inside these brackets. The true molecule never looks like any of the molecules inside these brackets. It always only looks like the average between the two. And you draw that special resonance arrow with one line and two heads that tells you take the average. It does not tell you equilibrium, right? Don't confuse that with the equilibrium arrow, which has two lines and only one head on each of them, in each direction. This means the reactants are turning into products and also turning back into reactants at the same time. You dealt a lot with that in general chemistry too. This is a very different arrow. It means take the average of these two molecules. The true molecule doesn't look anything like either of them. So if we redraw our molecule, I've redrawn fingolimod there. Whenever you learn these resonance patterns, not only do you want to learn how to recognize it, you also want to learn what to do once you see it. How do electrons move to create the non-integer bonds there to help the electrons spread out? And here, what look like pi bonds just move over to what look like sigma bonds. You could draw this clockwise or counterclockwise. It doesn't matter what direction the red arrows go in. So here you could see they're moving counterclockwise. But you could draw them clockwise, it's just the same. So for example here, I could take these pi electrons and move them over to the sigma bonds next door to them. And in this case, I'm going clockwise around the ring. But like I said, you could just as well draw it counterclockwise. And when you redraw the molecule for a resonance structure, you can draw all of the sigma bonds. Those won't change. With resonance, we are just changing lone pairs or pi bonds, the positions of those. So once you draw all the sigma bonds, we can fill the pi bonds in, and notice what's going to happen is anywhere where we had a double bond, the electrons are moving away from there. That's going to become a single bond. Anywhere where we had a single bond in the ring, that's where electrons are moving to, that's going to become a pi bond. And so here we have a pi bond, here we'll have another pi bond, and then on the right side we'll have a third pi bond. So notice all the pi bonds switched places. And if you take the average of these two, all of the bonds in that ring would be a 1.5 bond. So these resonance structures are communicating a resonance hybrid, an average of these two. that has 1.5 bonds in the ring, and a special stability and rigidity there. So this fifth pattern is very specific. You're going to have alternating single and double bonds around a ring, and the double bonds just move to where the single bonds are.